Hello everyone. In this video, I will go through a general review for the Calc 2 Exam 1 review. This can be applied to 162 and 166. Some differences in, minor differences in the classes, but generally the concepts are the same. So first, uh, probably went through vectors, just general vectors, what it means, like 2D, 3D, vector multiplication, addition, all those things. And I will go through each of these points in detail in a second. All right, so second, from vectors, we have dot product and cross product, which are, vague ways to multiply the vectors together. And, what those mean, like how do you get angles from between two vectors, or what cross product mean to like areas or volumes of the vectors, right? And then um, your class probably went into calculating the area between curves, right? Between two curves, um, bound like the area bounded by like a top curve and a bottom curve, and applying calculus using integrals to calculate those. And then you move into calculating the volume by slicing and shells. So like that's like cylindrical shells, or using like dish and washer. Uh, and finally, right, there are like physical applications. So like spring force is a common one. Torque, or how to apply, like sometimes you have dot products and cross products that are used in physics and what those mean. So let's now dive deeper into each of these topics. So first of all, vectors. So vectors have both direction and a magnitude, right? So and number two here, right, we have a point P at origin and Q at 2, 3, right? PQ, we write it with an arrow on top, then it's the destination point minus the origin point, which will be 2 and 3, right? This vector will be 2, 3. Right, and then vector scalar multiplication, if you multiply, let's say a constant to the PQ vector I have, then you just multiply it in with each component, right? It would be 2a and 3a as the resulting vector. And right, multiplying -1 just reverses the vector, right? So we have it, and reversing like a vector PQ is the same as saying QP, right? It's going the other way with the same magnitude. So in this situation, it would be -2, -3. And then the length of vector, very important in all the other points, like dot product and cross product. It's right marked by the like the absolute value sign around the vector, and you can use the distance formula for that. And you can do square root of the components of the vector squared, right? It would be 2 squared plus 3 squared, which would be 4 plus 9 root 13. And then add and subtract, pretty simple. Add and subtract the components of the vectors, and that would be fun. And then so we have three-dimensional vectors. We just add k, right? First two are like I, j, and k, right? Are like, let's say, the units of the every single dimensions of the vectors. And then unit vectors have length of 1. So PQ, again, would just be the vector divided by the length of the vector. And this vector will have the direction pointed. It will be the parallel direction to PQ, but have a length of 1. And then there's shapes like spheres. Um, right, the spherical equation is something that you should memorize. Pretty easy to memorize, right? It's x minus the x coordinate of the center squared plus b, y minus b, which is the y component of the center, and then so on equal to uh, r squared being the radius, right? ABC is the center coordinate, right? Well, and when you calculate for like this formula, sometimes you might need to complete a square, so that's something you might need to know. Um, Sometimes you can just use the distance formula when he asks you what the radius is, right? If you're given a point and you're given the center, like a point, if you're given a center and a point on the sphere, then you can just use the distance formula to calculate for the radius. Moving on, dot product, pretty important. Uh, ooh, right, so let's say we have a vector of ABC and B vector of DF, right? The dot product is just the components multiply each other and then the sum of that multiplication. All right, so A times D plus B times E plus C times F. Um, and this will result in a scalar, so it will not have a direction, only a magnitude. So, um, in that sense, A times A dot B is same as B dot A. The order does not matter for dot product. And the other definition of the dot product is this, right? The length of A times length of B times the cosine of angle in between. So this is definitely one way you can calculate for the angle in between. If you're asked that, right? If you are given, let's say, vector A is like ABC and vector B as DF, right? You have this. You can calculate it through the first method, right? You can get the magnitude of the dot product, and then you can calculate for the length of each, and then the only unknown would be the theta, which is the angle between, right? And then sort of related to that, if you calculate the dot product of two vectors is 0, that means that those vectors are normal to each other, because when theta is 90 degrees, then cosine 90 will be 0, and that 0 will be here, and then everything will be 0. The last thing from dot product will be projections, right? When we have, let's say, projection of B onto A, right? Written this way, you have, I think the main thing to remember here is it's onto A, right? That means it's the final projection's direction is A, right? This, if you recall, is the unit vector up here, is the unit vector of A. So that gives us the direction, and this gives us the magnitude. So this part is a unit vector, and this part is the dot product over the length of A. And this is something that you should just know. You should know code and memorize. So moving on to cross product. This cross product of two vectors will end up in a vector, right? So the direction will matter. And that means that we have A cross B. It does not equal to B cross A. So you need to be aware of the order you're crossing things, right? So in that sense, the first definition of cross product is uh, the length of cross product is the length of each vector times sine of theta, which is also the angle between. This is also another way you can calculate for the angle between when you're given two vectors. And going back to vector A and vector B, right? Cross product is, let's say up here, right? Cross product is when you have A, let's see, A, B, C. I usually write it out in this way, D, F, and then I can say it's I as the unit vector of the first component, and then times, right? I ignore the first column here, and I write in matrix form and minus j being the second uh, component, and I ignore the second column, plus k, ignoring the third column. Right, remember that the second component is negative. Right, and then you do find the determinant of these. Right, so be bf minus ce minus j of af minus cd plus k of ae minus bd. Right, and then when you get all these out, this should be like, it should be a vector, right? This will be go here, this will be second, and this part, right? And the application of cross product, right? The area of a parallelogram, let's say A and B are drawn out here, can be calculated using cross product, and the length of cross product will be that total area, and I'll show you why. So let's say this is the parallelogram we have. I'm gonna draw down the height here. Right, remember that the first definition is the length times each other times the sine, right? So this equal to length of A times length of B times sine theta, where theta is right here. Right, if we say, if you look at this right triangle here, um, the length of A, which is here, times the sine of theta. Right, if we have length of A times sine of theta, and using the right triangle, we can say that that will equal to height, as sine is opposite over hypotenuse, right? So using this relationship, sine relationship, we can substitute the length of A times sine theta to h, and we have length of B times h. That is just, right, base times height, which is the area of a parallelogram. Right? This comes in really handy when you have, let's say, like a triangle that you're supposed to calculate the area with. Right? That's just half of the area of the parallelogram, which is half of the cross product, the length of the cross product, right? The area of this. So that is a very common question. Now, if you have two vectors, A and B, if their cross product is 0, that means that they look something like this, right? If I A here and B here, that means that they're collinear. They're in the same direction, and if you think about this, it sort of makes sense as the area, I mean the angle in between theta will be 0, right? And then the sine of 0 is 0. So all of the length, all of the cross product, the length of cross product will be 0. You can also calculate the length of like a parallel pipe. Looks something like, so you have 3 vectors, looks something like this. Doesn't really have to be like a cube or anything, just something that would sort of be described by like 3 vectors. If you do the cross product of 2 of them, dot the third one. And if that comes out to be 0, that means that they're all in the same plane. Now let's move on to region between the curves. So here we have 2 equations, f of x and g of x. Right, one is just a line, one looks like to be a parabola, but it doesn't matter what it is. For These we generally want to calculate for the a and b, right? The limits that they're bounded by, right? Where they intersect, and those will be our limits of integration, as in here. And for these, we want to do top minus bottom. So for x, dx, if we're going, let's say, this direction, right? The limits are going from a to b in the x axis, then we want to do the top equation. In this case, is f of x minus g of x, the bottom equation, and integrate of that, um, and you'll get the area in between, right? Sometimes, in this case, in the bottom, right, we have a g of x, that here the top and bottom is really itself, right? So it's a little bit complicated to do that because you have to split it into two halves and top and bottom minus itself, and then you do top minus bottom for this part, right? It would be two integrations. But if you look at it the other way, right? This is x and y. So if you do dy, then essentially what I like to do is just turn my head 90 degrees to the right. And imagine the x-axis as the y-axis, and then you can do top minus bottom that way, right? In this case, it would be right minus left if you're looking at right side up. But you have to, when you do dy, you have to write every single function in terms of y, right? In this case, it would be, so you have to write like x equal to y something, right? And then you can have y as all your variables, dy. Then the integration will make sense. And there will be top minus bottom, and remember to calculate for the intersects, and you'll be fine. Then let's move on to volume by slicing. So in this case, I have a usually these questions, you have like a general shape that you are given the function to, and the shape is moved along an axis, like a x-axis or whatever, and you're calculating the volume that this shape, increasing or decreasing um, in size will generate. So in this case, right, I have a triangle. Let's say it's something, the original graph is something like this, right? And for every single point, there's just a triangle going up, right? And then you get something shaped like that. So for these, we take it into very small slices, very tiny slices, where the the width of that slice is so small that we just call it dx. And then the volume of the slice in that case would just be the area of that triangle times that dx. Um, and and generally you want to know how to calculate for that area. So then you can multiply it by dx, and then you can integrate over all of that, right? Whatever the area may be times dx, right? Sometimes it might be a square or whatever. If it's square, it'll be like, y squared, right? Whatever y is, y might be like x squared, then you might have the area of that square will be x to the fourth, right? You just put x to the fourth here, and then you integrate over that. Moving on, volume by revolution, right? This might be hard to visualize if you don't know, if you it might be hard to grasp if you can't visualize it. So here I have a sine x graph, the red line, going from 0 to pi, right? And I'm saying that I'm going to revolve this around the x-axis. So we get something like a ball, It's a little bit like a ball. It's not a sphere. Um, but I've color coded small sections of each. Um, a very as the same as slicing, right? I have very thin slices of this graph, right? For here, like the light blue matches the light blue over here. You can kind of imagine this light blue is like a line, and then you just revolve it around like an x-axis, like all the way around, like 360 degrees, and then you get sort of like a circle, like a disc, with very thin disc, um, and that's what essentially is portrayed here. This light blue disc is the resultant of this light blue line, or um, this little rectangle with really thin um, width, right? And then here, the dark blue is a little taller, so in the resulting graph, it makes a bigger disk, right? And then same goes with the greens, right? And then you can imagine that there might be like a orange line here, or like a red line somewhere in the middle, but those adding all up will make the whole graph, right? So the general concept is the same, right? We want to calculate the volume for a single subunit, like a disk, and then we can integrate over all of that so we can get the whole volume. So, um, looking still at this part, generally the volume of the disk, right? It's you think about it, it's really just um the area of that circle times dx. Same thing as the slicing up here. It's the area of a circle times the dx, right? Area of the circle is just pi r squared. That r is essentially the function, right? It's the length of the line, and that length is sine x in this case, right? It would be pi sine x squared dx, and then you just integrate that over the limits you have, pi r squared, whatever your r is. Now going beyond that, usually you have a question where you have two lines, right? You ask, let's see, to integrate this area or revolve this area around um, the x-axis in this case, right? It will have something like a shape over here too. Right, in this case, you have something like a hollow cylinder, if you can kind of imagine that. Um, but from a side view, it looks something like this, right? It's bounded by the red line up here, and then the blue line in the middle, and then it's hollow all in the middle. And then up bottom, right, it will be blue line, and then red line. The green area is the substance. And then, to make this sort of uh, you could better visualize it, I drew like a side view, right? If you look into the hollow side, right? If I'm right here, I'm looking into this hollow cylinder, then this is the view, right? Here, the blue line is in the middle. It's bounding the middle hollow section, whereas the red line is the outside circle, and it's giving the the outer radius shape. So this is a more clear view of like a cross-sectional area where uh, it is very easy to calculate like this washer shape. Right. The area of the green, which we're interested in, it would just be the red area minus the blue area, which in this case will be pi r squared for red minus pi r squared for blue. And then it will be um, combining that, right? It will be the bigger radius, or the top equation radius, with pi r top squared minus r bottom squared, right? And that gives us the volume of a disk, right? Remember, it's the r top squared minus r bottom squared, right? And again, you can integrate that over the limits you have at dx, and that will give you the volume of the whole thing. Right? Sometimes, it might be easier with dy, right? If you have, again, like a graph like this, then, it might be easier to do a dy. But I think this definitely needs some practice. dy sometimes can get really confusing, um, and there's no better way than just practicing it. Right? And then sometimes you're asked to revolve around a line that's not like an axis. It's not like an x or y axis. It might be like y equals 1. That radius would just be whatever you're revolving. Let's say 1. Y equal to 1. That's 1 minus your f of x. Whatever your equation is. Um, sorry, that should be like radius squared as in here. Um, and then we move on to volume by shells. Right, this is another way to think about how to calculate the volume by revolving. And so this, I have a just a line here, probably something like y equal to x negative x plus 6. And I'm wanting to revolve this around the y-axis, as shown by the arrows here, and it will make something like a cone, like here. This is sort of like a top-down view, whereas all the colors still here are matching, right? So I have sort of like a center point. The origin is here, right? And then away, let's say R1, I meet the blue line, right? And then this cylinder here is what essentially, right? If I have the center here, this will be R1, and it will create something like a tall cylinder. This little line, or have a thickness of really small, let's say dx. And then same thing with the red line, just farther away, it has less of a height, so it's like it's smaller. It's bigger, but it's like shorter. So in this sense, we can take each one of these hollow cylinders, um, sort of like a can, right? There's like can of Coke. There's liquid. When we drink all the Coke out, there's just a really thin wall of aluminum, and that is essentially calculating that volume of the aluminum wall. Um, so if we unfold that wall, it would be, if you have H here, and um, then you can get the circumference, right? It would be 2 pi r, and this will be just be like a rectangular. I forgot the name for it, but you can calculate the volume of this by just doing the circumference times h times the width, which in this case will be dx. So the the volume of a cylinder then would just be 2 pi r h dx. That means that we can integrate of that over the limits, then we can get 2 pi x, in this case will be r, times the h, which is the f of x, is how tall this thing is how long the line away from the x-axis, and then dx, right? sometimes R can change, right? If you're revolving around something like, let's say, x equals -1, then you need to consider that it would be like x minus -1, as in it's the distance away from that uh, line of revolution. So that might be something to be careful of. Know what you're revolving around. And also, you can use DUI. Um, it's I don't think it's preferable, but sometimes you're asked to do so. And then you got to consider these lines are no longer sort of vertical; it's horizontal. And you got to write everything in terms of y. But the general concept is the same. If you can visualize this will be much simpler. Now we go into arc length. So arc length, um, say we have a function f of x, and the arc length of this would be um, just the integral of square root of 1 plus dy of dx squared. I'm not gonna go over why, because that's uh, a little bit hard to explain. But this is a function you should definitely memorize because it comes up not only in arc length, but also in surface area later. Right? Sometimes, when you do dy dx, the derivative of this function, it might be improper integral. So you can try using dy instead, right? Write everything in terms of y and plug it in. It will be dx dy, do dy. Maybe you'll find better luck. Um, and generally, these, since they're, you know, since it's like something squared inside of a square root, uh, U sub is the general tactic to solving these integrals. Right. The integrals up here might be a little more easily solved than these. You might have to just dust up on the U sub, um, and you'll be fine there. And surface area, um, for these, let's say I have a similar equation, let's say f of x here, that kind of look like that. If I'm revolving this around the x-axis, then we have something like a vase looking on like a vase on the side, and uh, right, we again we try to imagine this like calculus, so like split it into really small pieces, right? When we take this blue part out, this is kind of look like the cylinder again, where if we unroll this, it will be the circumference, right? It's 2 pi r times the little bit of that arc length, right? If we're doing, this is the arc length of the function. So using that logic, the surface area would just be 2 pi r, the radius in this case. It would be how far away, right, this thing is from the axis of revolution. In this case, is x-axis times the arc length formula. So yeah, arc length should be memorized. It's pretty important. Moving on to physical applications of integrals and vectors in general. So first, related to dot product, uh, when we're deal with like a force on an object that is the direction of the force is not the same as the movement of the object, then there is the actual work that's being done is not just simply the force itself times distance. Then you have to consider the force component, right? It's the component that is parallel to the object's velocity direction um, that is doing the work. So in this situation, you can use the dot product, um, which is essentially the force times cosine theta, with g is the angle in between, times d, which is just saying that the work is the dot product of the force and the distance, right? It's the distance that you're calculating the work over. For cross product, you can think of us relating to torque. For torque, um, uh, the general torque equation is force times distance times sine theta, which is the angle in between those, and that um, is basically just cross product. If you think about it, um, or actually it's all around. Usually would generally think about it as being sine, but it's essentially a cross product at work. And you want to make sure you cross distance, cross the force because direction matters in cross product. And this is point O as in here. Move on, mass. So you're given like a rod that has constant rho, which is this density. With a constant rho, then the mass of that object will be the unit density times how many units of length there is, right? So, but if you have like a non-linear or rather just like a non-uniform density, then if you have a function for that, you can just integrate that function over the distance, right? And then you can get the total mass of that object. And then more work. So work, if you have in the same sense as mass, if you have a non-uniform force over a distance, then you cannot simply do work equal to force times distance because that force is changing over the distance. So in that sense, if you have a equation for that force over the distance, you can then integrate the force over distance. Then that will be your total work. A good example of this is the spring force, right? The spring force is k dx, or k change in x, which is the spring constant times the distance, or rather the length of the spring um, that's changing from the original natural state of that spring, right? It's x minus x0. So if we put that into this function, then we will have kx dx, right? And then we no longer need a change in x because we are integrating over two numbers. Then so that then we that would just be our change in distance. And then the last one will be work, right, against gravity. Um, this uh, sometimes you have like the mass is changing as maybe you're pulling like a rope up a ledge, right? As you pull more rope, there's less rope to pull. Um, as it like in there's like less rope hanging on the side of like an edge or something, right? So that might be something that requires like an integral because the mass is changing, right? Generally, the force, um, the gravitational force is mg, right? G being 9.81 meters per second squared times the mass, right? So sometimes it might be the mass is changing or like the distance. If the distance is changing, that's just accounted in the integral. So generally it's just this equation. It just got to make sure you know like how the mass is changing and write the correct equation for it. Thank you for watching this video. The past exam archive and all the videos I did related to this exam will be linked in the description below. Please check them out if you're interested. Thank you.